In order to decide on bond polarity, we need to see electronegativities for what they are. It's a tendency of an atom to attract the shared electrons. Now you have to remember, if you look at periodic table, without numerical data, fluorine is the most electronegative. On a scale of 0 to 4, it's 4, the maximum, and cesium, the least electronegative, 0.7. And electronegativity depends on three factors. One is the size. Fluorine is extremely small, therefore the smaller you are, the higher your electronegativity. Then number of protons or nuclear charge compared to number of shells you have. And finally, the number of inner shells you have. The less inner shells you have, the stronger your electronegativity. Now, if we compare bonds, and for example, if I give you carbon monoxide, we assume we can do Lewis dot structure for that. As soon as the bonds are different, you should agree that they are polar. Then you go periodic table and you see oxygen is further to the left of carbon, therefore should be more negative. And this is how we show partial negativity. So it's a small letter delta, carbon being positive, oxygen being negative. Then we also show an arrow. The head of the arrow is toward the negative. The tail, we put a positive sign on it. And this arrow here represents a dipole moment. It's dipoles simply having two poles of like battery, positive and negative. So this arrow here, this represents a dipole moment. And it's a vector. You can calculate it eventually in college when you get there, but for time being, just be able to justify it picture-wise, the direction of polarity. Let's look at another molecule. For example, if I give you carbon dioxide, then we do the Lewis dot structure for that. Now the same thing happens. Oxygen is more electronegative compared to carbon. So this side, this is the dipole moment for this carbon. But on the other side, you have the same pull. So this is an example that bonds are polar, but the molecule is non-polar because it's asymmetrical. It cancels both sides. So polar bonds and non-polar molecule. Let's do another example. For example, if I give you CH2F2, now you have to be careful with this. If you put a picture like this as a plus, you might have the notion that this is a sort of a non-polar entity because they cancel each other out. But this is a wrong shape, so we have to also respect shapes eventually. The shape is actually tetrahedral, and the polarity is toward fluorine. So this is the direction of polarity, and sometimes we show a resultant going this way. So this is polarity. So it's a polar molecule. If I give you another example, if you do hydrogen cyanide, you will do Lewis dot structure. You come across to this. Now carbon and hydrogen, they almost have the same polarity, so this is almost a non-polar bond. But carbon compared to nitrogen, nitrogen is very electronegative. So the direction of polarity is this way. And the overall direction of polarity for this molecule, you could have put a larger line and say this is how it is. It's a polar molecule with polar bonds. So in order to decide on polarity, you have to respect electronegativity. The two elements are different from each other. We are going to say they are polar. The more negative, the more electronegative will pull the electrons more toward itself, and we show it with a dipole moment, an arrow.